So after finishing three different questions as three different little problems of example 1 right here, allowed me to make a closing note before we're completely done with example 1. But so if anyone now happen to notice after viewing all three different little questions in our example, then this one piece of information remains the same throughout the entire example 1. Sigma equals 0.15. This population standard deviation remained the same. And looking back on my screen right here, right after we finished question C right here, but question C, once again, we drew information out of some beginning information. And that beginning description of our example 1 remained permanently there throughout the entire example 1 we were learning. And so this highlighted information, here in question C, we use the same standard deviation, 0.15. In our question B that we've done previously, also we used that sigma, that standard deviation value being 0.15. And in our question A, we also had the exact same piece of information given from our beginning description of the problem. So once again, my point is we had a permanent sigma value that doesn't matter which question we were working with, we were using the exact same sigma value. And that's what allowed our formula to calculate margin of error to be z sub c multiplied with sigma divided by square root n. So the closing note I would like to point out here is that this entire example 1 that we finished is all about we're estimating or particularly we were calculating margin of error, but here's what to emphasize. With given sigma, because having a given sigma, then we were able to use this formula, and anyone after viewing the video lesson of mine on three different little questions of example 1 must notice that the exact same formula remains throughout all three different questions right here, because we had the same given sigma value. And so the entire example 1 is all about we were finding the confidence interval to estimate population mean, but we were particularly estimating with given sigma. And calculating margin of error, we use that sigma in our formula. All right, so let's now look at our example 2 as we are continuing to study about how to find a confidence interval to estimate a population mean value. And we're still studying about gas price, but let me spend some time reading our example 2. So before I start reading out loud my example 2, note that example 2 here, unlike example 1, did not start out with any beginning description. So every question of example 2, we will be having question A, question B, and question C similar to example 1. But my point now is that there is no beginning description, and every question of example 2 is one little problem on its own independently. So example 2, right at part A right here, our obtained sample on June 1st, 2020 had mean $1.69 and standard deviation 0.25. So at this point, let me make a quick note right here. After looking at how I did example 1 earlier, then anyone viewing this video should be familiar with that sample I was mentioning about. But in case you still want to have a look at the sample again, then here it is. Here's our sample on June 1st, 2020. It had 36 sample prizes collected nationwide. The mean calculated from this sample, that's where I call it the X-bar value, sample mean value being $1.69. And this sample also had a standard deviation, but this standard deviation here, I have to refer to that as a sample standard deviation, lowercase s equals 0.25. So again, back to the question. So that's all about the description of the information, the description of the sample. And now Using that sample, we want to construct a 90% confidence interval to estimate national mean gas price on that day using only our sample. And I use this term, I put in this term, only our sample, just to make everybody notice that this time we do not have any beginning description. Or in other words, we know nothing about our beginning population of gas prices, of national gas prices. And so the sample is the only thing we rely to. So now once again, let me go ahead and list the given information. So as far as given information, we had a sample, and our sample size was 36, as I showed on screen earlier. Our sample mean right from this sample is $1.69. But note that unlike example 1, I do not have a sigma value anymore. I don't have this information. But instead, I actually have a sample standard deviation being 0.25. But I cannot use a sigma symbol for this because this is only a standard deviation of a sample. This standard deviation belongs only to this sample. If we switch to a different sample, this standard deviation will appear to be a different value. And as usual, I have a confidence level being given at 90% here on my screen. And then once again, allow me to highlight all that given the other information. So we got a mean being $1.69 and a standard deviation 0.25. But how I recognize that on my screen, it's a sample standard deviation and it's a sample mean. So confidence level here is 90% confidence level, and in decimal, it's 0.9. Same goal, we are estimating mu because mu is unknown. Our population mean value is unknown. But what population mean value is this? Or what does mu represent? Mu represents the national mean gas price on June 1st, 20. All right, and so now we are ready for tackling down the problem. So I would like to make a big clarification note right here, but this time we don't have, or I'm saying we are going to be moving on without a given sigma. Right there at that little note. Let me put it in a red box to catch everybody's attention. But aside from that information I'm highlighting, then the concept of the interval remains the same. So ultimately, when we finally arrive at our final confidence interval, that it must be from where our sample means that we already had a value here. We're going to need to calculate a margin of error and add and subtract that margin of error from our sample mean value. Same concept remains here. So that means ultimately at the very end, our confidence interval is going to look like this, from where our sample mean, which is currently $1.69, we will be adding and subtracting some margin of error. Take a moment to think this time. Throughout the entire example 1, we were using this formula, z sub c multiplied with sigma over square root n for our margin of error calculation. But have a moment to think whether or not we can still apply this formula to calculate our margin of error any longer. And so now I'm pretty sure you have some thinking. So we can no longer. So the answer here is no longer this formula. That's what I mean. No longer applicable. Or we cannot use this formula. So simple reason. We can always calculate z sub c easily because we had a confidence level given in the question. We have sample size. We already had sample size indicate it, and we can easily find that out because these are our samples, so we can purposely count the sample size. But sigma, so now this sigma is what got this formula hung up right here. We don't have a sigma in this problem right here, so we cannot proceed with this formula because this formula to calculate margin of error requires a known sigma value. We are working, as what I emphasized earlier, in this problem, we are working without sigma. So we need a new formula. Margin of error in this situation, in this case right here, where we're estimating population mean without sigma, then the part where it requires sigma, now why don't we use S, the lowercase, the S, the sample standard deviation value instead. So how about S over square root of n? It will work not as accurately as how we use sigma, but S can get the job done as well. But now as soon as we switch from using sigma to S, then we no longer use Z sub C. We actually have to use a new value that I call the T sub C. And I will be giving some instruction of how to find the T sub C. So this is our new formula to calculate margin of error when we don't have sigma, when we're estimating without sigma. And before I move on, let's try to recognize some similarities between the two formulas. So if we had sigma given, then the margin of error would have been using this formula, Z sub C multiplied with sigma over square root n. And I remind anyone viewing this video about this formula we finished using throughout example 1. But so now in our case here, when we don't have sigma, when we're working without sigma, then see, S is playing the role in place of sigma. We're still dividing by, in that quotient, we're still dividing by square root of n. That's the similarity between the two. And we're still using some kind of standard deviation, but here is sample standard deviation instead of population standard deviation. And then I made it clear that as soon as we switched over to using sample standard deviation instead of sigma, then the Z sub C can no longer be used. We have to use T sub C as an equivalent. So I will have a different video to explain in details where the T value, the T scores come from. But T score a lot of time has value, any T score a lot of time has value close enough with Z value, and the way how it works is almost identically the same with the Z score. So T score is another kind of value similar to Z score, but it's just not exactly the same. And like I said again, allow me not to explain too details about where this T comes from, this T value comes from in this particular video, but that will be in a different video lesson. And so now if we're looking closer into this formula and about getting ready to use it for calculating our margin of error, then we realize that we already had sample standard deviation given here. We already had sample size given here. The only thing now is that I need to show everyone how to calculate the T sub C value. So here in this video, I will show how to calculate the T sub C, but I won't be able to explain in detail what exactly T value is, or how people came up with that using that T value. That will wait for a different video lesson. So here we go for T sub C. This is how we're calculating it. So how to find T sub C. This is more like a general instruction right here. But step 1, again, I am going to go 0.5, adding with half of my confidence level. So 0.5 plus 0.9 over 2, that gives me 0.95. And again, I'm referring to this as an area left. And in addition to what I explained earlier, T-score does have a distribution curve looking almost like the standard normal distribution. So like I said, the distribution of T-scores looks almost identically the same with the standard normal distribution. So all of these values are T-scores. So T sub C is somewhere And this area is indicating that the area accumulatedly to the left-hand side is going to be 0.95. And then step 2 now, I am going to calculate, for the first time I'm introducing what's so-called the degrees freedom. So any sample that we're using has a degrees of freedom. So the degrees of freedom here, I'm going to use a shorthand abbreviation DF, that stands for degrees of freedom. So for any sample, the degrees of freedom comes out to be the sample size minus 1. So in our case here, it's 36 being our sample size, we're subtracting 1. So this sample that we are using will have a degrees of freedom being 35. And that's our degrees of freedom. And the last step now is to calculate our T sub C. So what I need to run now is, instead of INVZ program, now I am going to introduce a different program, and also there are programs out there over the web to serve the similar functionality right here, but we're inverting a left area, but what we want to come out with is a t-score. So here that I designed my program that's called INVT, but the INVT program this time will ask for 2 information. The first information it asks for is the area left. So 0.95 is the first thing you're giving it, you're providing it, and the next information your INVT program is asking for is the degrees of freedom. So the degrees of freedom here, I'm providing 0.35. That's why in a written notation, I'm writing INVT in parentheses 0.95, 35, meaning we have to provide these 2 values when you run any INVT programs. And of course, it will always ask for, a lot of times it asks for the area left first, and then the step after is asking for degrees of freedom. But after running the INVT program, the answer you would have there is your T sub C value. So on my screen here, allow me to show you how to run my INVT program that I wrote right here. But so on the Microsoft Excel screen, on the Microsoft Excel file, there's that tab at the bottom say INVT. So all you do is just click on that to navigate over to INVT program. And so it has 2 boxes here where you're gonna be able to enter your 2 specific value. So our area left here is 0.95, and then you can just hit the right arrow key and switch over to the other box that's saying degrees of freedom. So our particular problem here, we are using a sample with degrees of freedom 35. So I'm putting 35 here, and I'm hitting enter. So now this value here is my final t-score. So T sub C here, I also use, a lot of times I use a T sub C to be in 3 decimals. But every problem that anyone attempting throughout your assignments will have different rounding requirements for T sub C. But so here in this lecture, I am going to go with 1.6, and to round to 3 decimals, then I'm forced down to, in this case, 69. That's my only choice left. So that's my T sub C. And so now I am ready to calculate my margin of error, with T sub C being calculated to be 1.69. I'm substituting T sub C with 1.69, and then T sub C is multiplied with sample standard deviation in our case here being 0.25, and our sample size is 36, so square root of 36. And now I'm ready for final calculation. So it comes out to be 0.0704, and a lot longer. And again, we're still studying about gas price, and gas prices in our nation is in 2 decimal places. So I have my legitimate reason here to round this answer to 2 decimals. So 0.07, or it's about 7 cents to be my margin of error. So now at this point, my final confidence interval is ready. So this confidence interval is telling me that from where my sample mean value. So it happens to be that our T sub C score is also looking exactly like our, as far as value, it's looking exactly like our sample mean. So it might easily cause some confusion. But here I'm about to use my sample mean value. And then back to what I was saying earlier, then the final confidence interval in our case here would be anywhere from our current sample mean. We are going to add and subtract our margin of error that we calculated previously to be 0.07. And this interval is our final confidence interval being guaranteed at 90% confidence level. And as an interpretation of this confidence interval, now this time completely without knowing sigma value, but we can still estimate. And so we can now say that our unknown national mean gas price on June 1st, 2020 happened anywhere 7 cents up and down from our obtained sample means on that day being $1.69 here. And this estimate is guaranteed at 90% successful level or confidence level. And again, for anyone who's not comfortable with looking at a confidence interval in this format right here, you always have your choice to subtract the margin of error from your sample value, and that gives you a low end being $1.62. And you can once again add this margin of error to your sample value in the center of the interval to produce a high end of your interval. So $1.76 in this case is the high end of your interval. And so again, what it says here is that our unknown national mean gas price on June 1st, 2020 is estimated to be somewhere inside of this interval between the low end $1.62 and the high end $1.76, guarantee at 90% confidence level. And this interval right here is once again what I refer to as the confidence interval in traditional format.